I'll be presenting nuclear fusion. Nuclear fusion is the process of combining light elements into heavier elements, and it's also known as nucleosynthesis. Nuclear fusion requires high-speed collisions and high temperatures, and a great amount of energy is released in nuclear fusion due to the greater binding energy of the daughter nucleus, and wherein the daughter nucleus is basically the nucleus remaining after the decay. So as it can be seen in the binding energy per nucleon diagram, which is given on the right, the elements on the left side experience nuclear fusion to attain the most stable amount, which is demonstrated as the blue line. So because they're below the stable amount, they have to combine to reach that. So this makes quantitative sense, as I said, since the amount is greater than each element's individual binding energy per nucleon. So they have to combine. And the elements on the right-hand side, however, experience nuclear fission, which is basically the opposite of nuclear fusion. And it's this splitting of a heavy nucleus into two lighter nuclei. And again, this quantitative reasoning can be applied because the elements are heavy and they need to split to go back in the trend to achieve this optimum value. So the image provided below is a depiction of nuclear fusion. So as it can be seen, the two atoms are colliding, in this case, two hydrogen atoms, and they're creating a new atom with higher mass. And in this case, it's a helium atom. It has two protons and one neutron, so it's heavier. And as a product, a neutron is released to balance both sides of the equation. So the following is an example of equation of a nuclear fusion reaction. So as it can be seen again, two atoms with less atomic mass, in this case, two hydrogen isotopes, combine and give yield to an atom with higher mass, in this case, a helium. So as a product, a nucleus is also produced to balance the overall equation, or the addition of mass values on both sides wouldn't be equal. So looking at the energy released, 17.59 mega electron volts is released, and the value is very high, especially compared to energy released from a nuclear fission reaction. So harnessing power from nuclear fusion. So as aforementioned, the energy released from a nuclear fusion reaction is considerably high, and it's almost quadruple the amount released from nuclear fission. Likewise, unlike nuclear fusion doesn't produce long-lived radioactive waste. And since it's both better for the environment and it yields a great amount of energy, it is ultimately the optimum reaction. However, unlike nuclear fission reactions, nuclear fusion is only proposed and has not been used as a source of energy yet, as it's extremely challenging to execute and it's considered as the grand engineering challenge. So in a controlled nuclear fusion power plant, three conditions must be fulfilled. First of all, a very high temperature, which would be over 100 million degrees Celsius, to provoke collisions of highly energetic particles. Secondly, sufficient particle density in the plasma, essentially where the reaction takes place, to increase the probability of these collisions. And finally, a sufficient confinement to hold the plasma and enable the fusion reactions to take place on an ongoing basis. So here the image depicts a theoretical nuclear fusion reactor. However, this is only theoretical, as I said before, it hasn't been executed yet. So to date, the confinement concept with the best results has been the tokamak, a donut-shaped configuration first invented in the 1950s, which uses powerful magnets to contain the plasma. Tokamak machines can already provide the essential conditions for fusion in terms of both plasma density and the required temperature, and fusion reactions can be generated. So what's still missing is to ensure the production of net power is better and longer confinement, which is a measure of how good the magnetic field is at maintaining the plasma energy time. So this is only proposed. They have built the machine. However, this hasn't been used as a source of energy for anything. And the image provided below, the one on the left, is again a theoretical concept that explains how the tokamak specifically works, as each section is highlighted. And the one on the right is a physical image of the tokamak. So ITER, in other words, International Fusion Energy Organization, is a collaboration between 35 countries, and it will be the largest fusion experiment on Earth. It is currently under construction in Saint-Paul-les-Durance in France, and it's scheduled to become operational at the end of 2025. So ITER is designed to demonstrate much higher gains in fusion power than other fusion experiments conducted to date. And following the injection of 50 megawatts of heating power, it aims to produce 500 megawatts of thermal power for long pulses of 400 to 600 seconds. And even though ITR will not capture the power it produces as electricity, it will definitely pave way for a machine that can. And below are images of the construction site of ITER. So the next stage after ITER is converting heat into electricity, which will be addressed by a demonstration fusion power plant known as DEMO. So DEMO is expected to explore and demonstrate continuous or near continuous operation, fuel self-sufficiency, and large-scale production of energy, including its conversion to electricity, and it could be connected to power grid by approximately 2050. So again, below is a theoretical conceptual demonstration, the image. As you can see on the right, it is connected to a power grid. So nuclear fusion and astrophysics. The temperatures in the core are much higher than on the surface of a star. And the main process for energy production in a star is nuclear fusion of hydrogen to helium. So this is the process that occurs during most of a star's lifetime. And after the hydrogen in the star's core is exhausted, the star can burn helium to form progressively heavier elements like carbon and oxygen and so on, until iron and nickel are formed. So up to this point, the process releases energy, and the formation of elements heavier than iron and nickel requires the input of an energy. So supernova explosions results when the cores of massive stars have exhausted their fuel supplies and burned everything into iron and nickel. So the nuclei with mass heavier than nickel are thought to be formed during these explosions. And the images on the upper right represents our sun, which is a star, and below is a scientific depiction of what a star actually does. As it can be seen, the temperature of the outside is around 6,000 Kelvin, whereas inside it's much higher, and there's thermonuclear reaction going on, and it's just depicted and highlighted. So all stars follow a simple proton-proton cycle in order to maintain equilibrium between gravity and pressure. So when the star is expanding, it rises in temperature and therefore rises in pressure. So this is required in order to keep a balance between the force of gravity that is trying to compress the star. So at the beginning of a star's life cycle, the star consists of mainly of hydrogen, and in fact, they are 98% made of hydrogen. So there are three basic stages of the proton-proton cycle. So firstly, two hydrogens fuse to form deuterium plus a positron and a neutrino. And each positron is annihilated to create two gamma particles, which are in turn absorbed and re-emitted as 200,000 photons of light per gamma particle. So secondly, a deuterium and a hydrogen fuse to create helium and a gamma particle. Another deuterium and a hydrogen fuse to create helium and a gamma particle. Thus far, there have been 4 gamma particles created with 800,000 photons of light. That's one bright star. And finally, 2 helium atoms fuse to create a heavy helium atom. Once the hydrogen in the star runs out, it begins to consume the created helium from the hydrogen reactions. So based on the star's color, you can actually find out what type of fuel it's consuming. And this is where the Hertzsprung-Russell diagrams were derived from. And the images below basically depict this. So as you can see, gravity is trying to push a star in, whereas fusion is contradicting that force and maintaining a balance. And the image on the right is just the equation formats of the stuff we discussed, like hydrogen plus hydrogen forming deuterium plus electron and neutrino, and so on. And these are the citations for this presentation. Thank you for listening.